Look up at the night sky on a clear evening. You see those countless points of light, a vast and silent ocean of stars. For centuries, humanity has gazed upon that same view, asking one profound, persistent question: are we truly alone in the universe? That question, once the domain of philosophers and science fiction writers, has now moved firmly into the realm of science. We are living in the golden age of a cosmic search, a thrilling endeavor that is reshaping our understanding of our place in the cosmos. This is the exciting field of astrobiology, the study of life in the universe, and its primary mission is to find an answer. Think of it as the greatest treasure hunt in history, but on a galactic scale. Instead of a dusty map, astronomers use powerful telescopes as their guides. Their treasure isn't gold or jewels, but something infinitely more precious: another world orbiting a distant sun that possesses the right conditions for life to arise. These distant planets, known as exoplanets, are the targets. For a long time, we could only wonder if other planets existed beyond our solar system. Today, we know they are not the exception but the rule. Stars with planets are the norm, and the number of known worlds is staggering, opening up a universe of possibilities that our ancestors could scarcely have dreamed of. This journey we are about to take together is a voyage to the frontiers of that discovery. We are going to explore 30 of the most promising, most fascinating planets that scientists believe could potentially support life. These are not just dots of light. These are entire worlds with their own unique characteristics. Some might be water worlds covered in global oceans. Others could be super-Earths with mountains that dwarf our own Himalayas. We will delve into the science of what makes a world habitable, from the delicate balance of temperature to the presence of key ingredients like liquid water. So get ready to leave our solar system behind and embark on an adventure across light years of space to visit 30 worlds that just might be home to our cosmic neighbors. The search for a second Earth is on, and what we are finding is more incredible than we ever imagined. Our journey to these 30 worlds begins right on our cosmic doorstep with the closest known exoplanet to Earth, a place called Proxima Centauri b. Imagine a planet so near in the grand scheme of the galaxy that the star it orbits is visible to the naked eye from the southern hemisphere. This isn't a world dreamed up for a film. It's a real, rocky planet with a mass remarkably similar to our own, and it's located in the habitable zone of its star. That term, habitable zone, is often called the Goldilocks zone, not too hot, not too cold, but just right for liquid water to potentially exist on the surface. And the existence of liquid water is the single most exciting clue in our search for life. Proxima b represents our first, best hope that another living world could be practically next door, a mere 4.2 light-years away. But this promising neighbor comes with a set of extraordinary challenges that paint a very different picture from our own sunny existence. Proxima Centauri b orbits a red dwarf star, a type of star that is far smaller, cooler, and more tempestuous than our Sun. If you were to stand on the surface of this planet, the sky would be dominated by a deep crimson orb, casting a perpetual twilight glow across the landscape. The first major challenge is tidal locking. It's very likely that Proxima b, like our moon is to Earth, has one side permanently facing its star, bathed in eternal daylight, while the other is plunged into an endless, frigid night. The only place temperate enough for life as we know it would be a narrow band along the terminator line, the twilight zone between these two extreme hemispheres. The second, and perhaps more dangerous, challenge comes from the star itself. Red dwarfs are notorious for their violent outbursts. Proxima Centauri is a flare star, capable of unleashing enormous eruptions of radiation that would bombard the planet with X-rays and ultraviolet light. A flare powerful enough could potentially strip away a young atmosphere, evaporate oceans, and sterilize the surface. So the central, gripping question scientists are debating is this: could Proxima be hold onto a protective atmosphere? An atmosphere is a planet's shield. It regulates temperature, protects from radiation, and is essential for the chemistry of life. Some models suggest that the relentless stellar activity might have scoured the planet bare billions of years ago. Others propose fascinating scenarios where a thick atmosphere or a global magnetic field could deflect the worst of the star's fury, or where life, if it exists, might have found a way to thrive deep underground or beneath protective layers of ice. The discovery of Proxima Centauri b was a monumental moment, proving that potentially habitable worlds can form in our immediate stellar neighborhood. But it also taught us that habitability is a complex and fragile balance, even on a world that seems at first glance so much like home. If Proxima b shows us the challenges of a solitary world around a fiery star, our next destination reveals an entirely different cosmic architecture, one of breathtaking planetary abundance. Just 39 light-years from Earth lies a star system that shattered our expectations of what is possible. TRAPPIST-1, an ultra-cool dwarf star so faint it's barely larger than the planet Jupiter, is home to a family of not one or two but 7 known Earth-sized worlds. And of these 7 siblings, the 4th planet out, known as TRAPPIST-1e, stands out as perhaps the most promising candidate for habitability we have yet discovered. This isn't just finding a needle in a cosmic haystack, it's finding an entire sewing kit. What makes TRAPPIST-1e so compelling is its position right in the heart of the system's habitable zone. Calculations suggest it receives a similar amount of stellar energy from its dim red sun as Earth does from ours, making the existence of liquid water on its surface a very real possibility. Its density tells us it's almost certainly a rocky world, much like our own, and its size is so similar to Earth that you could almost call it a twin. But the similarities might end there. Imagine a sky where the star is a deep, dull red, like a cooling ember, casting a perpetual sunset hue across the landscape. And in that sky, you wouldn't see just one moon. You would see the other planets of the system, some appearing as large as our own moon, drifting past each other in a silent, majestic dance. The view from TRAPPIST-1e would be a constant reminder that you are part of a crowded planetary neighborhood. This crowded nature is precisely what gives scientists an unprecedented opportunity. The entire TRAPPIST-1 system is tilted almost perfectly edge-on from our perspective. This means that as each planet transits or passes in front of its star, we can observe the starlight filtering through its atmosphere. It's like seeing a distant city skyline at night. You can learn a lot from the silhouettes of the buildings, but if you see the glow of specific lights in the windows, you can start to deduce what's happening inside. With powerful telescopes like the James Webb Space Telescope, astronomers are attempting to do just that, to analyze the chemical fingerprints in the light that passes through TRAPPIST-1e's air, searching for the telltale signs of gases like oxygen, methane, or carbon dioxide that could hint at biological processes. The profound significance of the TRAPPIST-1 system goes far beyond any single world. For the first time, we have confirmed that multiple Earth-sized planets can coexist in the habitable zone of the same star. This opens up incredible possibilities. If conditions are right on TRAPPIST-1e, could they also be favorable on its neighbors, TRAPPIST-1f and TRAPPIST-1g? We are no longer asking if a single planet in a system can be habitable, but whether entire planetary systems can become cradles for life. This discovery suggests that life, if it exists, might not be an isolated phenomenon, but could potentially arise on several worlds within the same stellar family, a concept that fundamentally expands our imagination of what a living universe might look like. Moving outward in the remarkable TRAPPIST-1 system, we encounter the next pair of Earth-sized siblings, TRAPPIST-1f and TRAPPIST-1g. While TRAPPIST-1e sits in what we might call the prime real estate of the habitable zone, these two worlds explore the outer and inner boundaries of that life-friendly region, showing us how conditions can vary dramatically even within the same planetary family. TRAPPIST-1F, the fifth planet from its star, is a cooler world receiving less stellar energy. It exists on the habitable zone's outer fringe, a place where any surface water would be perpetually cold, potentially leading to a global ice-covered ocean, much like the icy moons in our own solar system. If this world has a thick atmosphere rich in greenhouse gases, however, it could trap enough heat to maintain vast, liquid oceans beneath a thin crust of ice or even on its surface. It represents the possibility of a water world in a deep freeze, where life might cling to existence around hydrothermal vents on the ocean floor, completely isolated from the dim red sun above. In stark contrast, its neighbor, TRAPPIST-1G, is larger and receives significantly more energy, placing it on the warmer, inner edge of the habitable zone. This position comes with its own set of challenges. A planet this close to its star risks experiencing a runaway greenhouse effect, where temperatures soar, causing any oceans to evaporate completely and leaving behind a scorching, Venus-like world. The fate of TRAPPIST-1G likely hinges on the composition of its original atmosphere and the history of its star's activity. Did it form with a moderate atmosphere that allows for temperate conditions, or was it doomed from the start to be a hothouse? The fascinating duality of these two planets, one potentially an icy ocean world and the other a warmer, perhaps even arid planet, demonstrates the fine line that separates a habitable world from an uninhabitable one, even when they orbit the same sun. What makes the relationship between these two worlds, and indeed the entire TRAPPIST-1 system, truly extraordinary is a concept known as panspermia. In our solar system, planets are separated by vast distances. The idea of a meteorite from Earth carrying microbial life to Mars is plausible, but the journey to Jupiter's moon Europa is far less likely. In the TRAPPIST-1 system, the planets are packed incredibly close together. The distance between TRAPPIST-1F and TRAPPIST-1G is smaller than the distance from Earth to our moon. This proximity means that a major asteroid impact on one world could easily eject material containing hardy microorganisms out into space, and the gravitational pull of its neighboring planet could readily capture that material within a relatively short period. This opens up the revolutionary idea that life, if it ever arose on just one of these worlds, perhaps the perfectly positioned TRAPPIST-1E, could have been shared with its siblings. This process of interplanetary seeding could mean that the TRAPPIST-1 system isn't just a collection of individual worlds, but a single, interconnected biological environment. Instead of life having to start from scratch independently on each planet, it might have hopped from one to the next, adapting to the different conditions on each. Life on the cooler TRAPPIST-1F would have evolved to survive in a deep, dark ocean, while life on the warmer TRAPPIST-1G might have adapted to a potentially thinner atmosphere and stronger stellar radiation. The discovery of life on one of these worlds would immediately make its neighbors the most compelling targets for exploration in the entire galaxy, because we would have strong reason to suspect that life exists there too, having traveled the short cosmic distance between them. This transforms the system from a set of separate possibilities into a potential archipelago of life, a miniature cosmos where biology could have spread its seeds across multiple worlds. While the TRAPPIST-1 system revealed a whole family of potential Earths, the discovery that truly opened the floodgates and proved such worlds were not just a rarity came from NASA's Kepler space telescope. Its crowning achievement in the search for habitable worlds was the identification of a planet called Kepler 186f. This wasn't just another exoplanet, it was a landmark moment in history, the very first rocky planet we ever found that was almost exactly Earth size and orbiting comfortably within the habitable zone of its own sun. Before this discovery, we knew of larger, gas-dominated planets in the habitable zone, often called super-Earths, but finding a world so similar in scale to our own was the crucial piece of evidence that shifted the search from theoretical possibility to tangible reality. Kepler 186f orbits a red dwarf star, a category that is becoming a familiar theme in our search. It's slightly larger than Earth, but only by about 10%, placing it firmly in the category of a terrestrial, rocky world rather than a gaseous mini-Neptune. Its year is much shorter than ours, lasting only 130 Earth days, as it circles its star much more closely than we orbit the Sun. But because its star is a cooler red dwarf, that close orbit still places it right in the middle of the star's habitable zone, where temperatures could allow for liquid water. The planet is likely tidally locked, with one side in permanent daylight and the other in eternal night. But its slightly larger size gives scientists hope that it might possess a robust atmosphere capable of distributing heat around the planet, potentially creating a temperate band in the twilight region between the two extremes. The profound impact of Kepler 186f's discovery cannot be overstated. It was the definitive proof that planets like ours are not unique anomalies. The Kepler mission taught us that small, rocky worlds are incredibly common throughout the galaxy, and Kepler 186f demonstrated that a significant number of those worlds reside in the Goldilocks zone. This single finding transformed the central question of astrobiology. We were no longer asking if Earth-sized habitable zone planets existed. We were now asking how many there were and what specific conditions made them truly livable. It provided a massive statistical boost to the idea that the ingredients for life are widespread, fueling optimism that we might one day find a world not just similar in size, but similar in every way to the vibrant, life-filled planet we call home. As we continue our journey from the landmark discovery of Kepler 186f, we encounter a world that many scientists consider an even stronger candidate for a true Earth analog. Meet Kepler 442b, a planet that doesn't just check the basic boxes for habitability, but appears to do so with impressive scores across the board. Discovered by the Kepler telescope in its extended mission, this world has steadily climbed the rankings to become one of the most Earth-like exoplanets we know of, offering a tantalizing glimpse of what a slightly larger, yet potentially very familiar planet might be like. Let's break down what makes Kepler 442b so special. First, its size. This planet is a super-Earth, but only just, with a radius about 1/3 larger than our own world. This is a crucial distinction. While some super-Earths can be massive enough to hold onto thick, crushing hydrogen atmospheres, becoming more like mini-Neptunes, the data on Kepler 442b strongly suggests it falls below the threshold where that is likely. Based on statistical models of how planets form, there is a very high probability, significantly higher than for many other candidates, that Kepler 442b is a terrestrial world with a solid, rocky surface you could theoretically stand on. It would have stronger gravity, to be sure, but not so strong as to make surface conditions unimaginable for life. Perhaps the most significant advantage Kepler 442b holds over many other promising worlds is the star it calls home. Unlike the red dwarf or M-type stars that dominate our list, Kepler 442b orbits a K-type star, often called an orange dwarf. This is a quieter, more stable, and arguably more life-friendly environment. While our Sun is a G-type star, a K-type star is slightly smaller, cooler, and longer-lived. This extended lifespan, potentially lasting tens of billions of years, offers a much wider, more stable window for life to emerge and evolve into complex forms. Furthermore, K-stars are far less volatile than their M-dwarf cousins. They don't produce the frequent, violent flares that can bombard close-orbiting planets with sterilizing radiation, threatening to strip away atmospheres and scupper the chances for life before it even begins. The planet's position relative to this stable star is another point in its favor. Kepler 442b orbits within its star's habitable zone, but the specifics are fascinating. It receives roughly 70% of the sunlight that Earth gets from the Sun. At first glance, that might sound too cold, but it's a figure that sits well within the range of possibility. With a suitable atmosphere that contains greenhouse gases like carbon dioxide, this level of insulation could be perfect for maintaining a comfortable Earth-like temperature. It's a scenario that could avoid the twin pitfalls of a runaway greenhouse effect on the inner edge of the zone and a global deep freeze on the outer edge. This places Kepler 442b in what might be considered the sweet spot for long-term climate stability. While we cannot yet determine if it has an atmosphere or liquid water, the fundamental ingredients, a likely rocky composition, a stable stellar parent, and the right amount of stellar energy are all aligned in a way that makes Kepler 442b one of the most compelling worlds on our list for future study. Leaving Kepler 442b behind, we venture to another remarkable discovery from the Kepler telescope, one that presented us with not just one, but two promising worlds orbiting the same star, a system that echoes the planetary abundance of TRAPPIST-1 but with a different twist. The star is Kepler 62, slightly smaller and cooler than our Sun, and its two outermost planets, designated Kepler 62e and Kepler 62f, have captured the imagination of scientists as quintessential examples of super-Earths within the habitable zone. The term super-Earth can be a little misleading. It doesn't necessarily mean these planets are Earth-like, only that they are larger than Earth but smaller than the ice giants Uranus and Neptune. This size range is incredibly common in our galaxy, yet it encompasses a stunning diversity of worlds, from rocky planets with continents and oceans to water worlds or even gaseous mini-Neptunes. Kepler 62e and f sit at the heart of this mystery. Kepler 62e, the inner of the two, is a world about 60% larger than Earth. It orbits comfortably within the inner part of its star's habitable zone, receiving a bit more stellar energy than Earth does. Based on its size and density estimates, many planetary scientists believe this planet could be what's known as an ocean world or water world. Imagine a planet with no visible landmasses at all, a globe entirely shrouded by a deep, planet-wide ocean, perhaps hundreds of kilometers deep. Beneath a thick atmosphere, the surface would be a single, endless sea, with pressures at the bottom that are almost unimaginable. While this might sound like a desert for life as we know it on the surface, the ocean itself could be a rich soup of chemistry. The deep abyss could host ecosystems around hydrothermal vents, similar to those in Earth's oceans that thrive in complete darkness independent of sunlight. The possibility of a global ocean makes Kepler 62e a fascinating, if alien, candidate for habitability. Its sibling, Kepler 62f, is slightly smaller and orbits further out on the cooler outer edge of the habitable zone. It receives much less sunlight, so its fate is critically tied to the nature of its atmosphere. If Kepler 62f has a thin atmosphere like Mars, it would likely be a frozen wasteland. However, if it possesses a thick atmosphere rich in greenhouse gases such as carbon dioxide, that atmosphere could act as an insulating blanket, trapping enough heat to maintain liquid water on the surface. This scenario could make Kepler 62f a more temperate world, perhaps even one with both liquid water and exposed land, offering an environment that feels more familiar to us. The stark contrast between these two sibling planets, one a potential global ocean heated from within and by its star, the other a potentially colder world kept warm by its own air, showcases how two worlds around the same sun can evolve down dramatically different paths. Now let's turn our attention to a third Kepler discovery, Kepler 69c, which orbits a star much more similar to our own Sun. This planet serves as an important cautionary tale and a lesson in the evolving nature of exoplanet science. When it was first discovered, Kepler 69c was heralded as one of the most Earth-like planets found, a super-Earth in the habitable zone of a Sun-like star. However, as scientists collected more data and refined their models, the picture became less clear. Kepler 69c is significantly larger than Earth, with a radius about 70% greater. This places it right on the borderline where a planet may stop being a solid, rocky super-Earth and start becoming a mini-Neptune, a type of planet that has no solid surface but instead a deep, massive atmosphere of hydrogen and helium over a possible layer of high-pressure ices or a rocky core. A visitor to Kepler 69c would not find a surface to land on. They would be crushed by immense atmospheric pressure long before reaching anything solid. The ongoing debate about Kepler 69c's true nature is a perfect example of how our understanding of these distant worlds is constantly being refined. Its position in the habitable zone is still significant, but if it is a mini-Neptune, the definition of habitability shifts entirely. Life as we know it requires a surface or, at the very least, a boundary between a liquid and a solid, like the ocean floor. A gaseous world lacks such an environment. However, some theories suggest that even a mini-Neptune could host a deep layer of liquid water under its atmosphere, a global ocean so vast it dwarfs all of Earth's water combined, but sealed away under incredible pressure and darkness. While this is a much more speculative idea, it reminds us that the potential for life may exist in forms and places we are only beginning to conceive. The trio of Kepler 62e, Kepler 62f, and Kepler 69c together illustrate the broad spectrum of what a habitable world might mean, from watery abysses to temperate rocky planets to enigmatic gaseous worlds, each expanding our definition of what is possible in the cosmos. Shifting our gaze from the Kepler systems, we arrive at a world that astronomers describe not just as promising, but as a heavyweight champion in the most literal sense. Located about 49 light-years away in the constellation Cetus, LHS 1140b is a super-Earth that stands out for its incredible density. This isn't a puffy, gaseous world. It's a massive, compact sphere of rock and metal, a planet so dense that scientists believe it must have a colossal iron core. Think of it as a planet that is far more massive than Earth, yet not much larger in physical size, resulting in a world where gravity would be significantly stronger and everything about its structure is amplified. This remarkable density is the key that unlocks its potential as one of the most intriguing habitable zone planets we've ever found. What makes LHS 1140b so compelling is how its physical makeup directly influences its potential for life. Orbiting a calm red dwarf star within the habitable zone, the planet's high density suggests a crucial advantage, a powerful gravity well capable of holding onto a substantial atmosphere over billions of years. For planets orbiting active red dwarfs, retaining an atmosphere is the primary battle. Violent stellar flares and intense radiation can easily blast away the air from a smaller, less massive world, leaving it a barren rock. But LHS 1140b, with its strong gravitational grip, is like a fortress. It likely has the strength to cling to a thick, protective blanket of gases, which would serve as an essential shield against its star's outbursts. This atmosphere would not only protect the surface from harmful radiation, but also distribute heat, potentially creating stable conditions where liquid water could pool and persist. This very possibility is what has placed LHS 1140b at the top of the target list for the most powerful space telescope ever built, the James Webb Space Telescope. JWST has the unique ability to analyze the chemical composition of a planet's atmosphere by observing the starlight that filters through it during a transit. For LHS 1140b, astronomers are eagerly awaiting data that could reveal the presence of key gases like nitrogen, oxygen, carbon dioxide, or even methane. The detection of such biomarkers would be a monumental step, providing the first concrete hints that the conditions for life might not just be theoretically possible but actually present. The planet's large size and frequent transits make it an ideal laboratory for these cutting-edge observations. We are on the cusp of potentially peering into the air of another world in the habitable zone and learning whether it contains the basic building blocks we associate with a living planet. The story of LHS 1140b is a powerful reminder that in the search for life, sometimes the most promising candidates are not the ones that look most like Earth, but the ones that have the fundamental strength to protect and sustain a world of their own. Now, let's journey to a world that has recently catapulted from being just another name in a catalogue to one of the most talked about exoplanets in astronomy. This is K2-18b, a planet that challenges our Earth-centric view of habitability and introduces us to a completely new and exotic class of world. Located about 120 light-years away, K2-18b is not a rocky super-Earth like many we've discussed. It's significantly larger, with a radius more than twice that of our planet, placing it in a category that scientists are now calling a mini-Neptune. For a long time, planets of this size were largely written off in the search for life, as they were assumed to be gaseous balls with no solid surface, hostile to biology as we know it. But K2-18b and the revolutionary concept it represents has forced us to completely rethink those assumptions. The breakthrough came with observations from the James Webb Space Telescope, which performed a detailed chemical analysis of this distant world's atmosphere. What it found was nothing short of spectacular. Scientists detected the clear signature of water vapor, along with molecules of carbon dioxide and methane. This is the first time we have ever identified carbon-bearing molecules in the atmosphere of a planet orbiting within the habitable zone of its star. It's a detection that suggests this world possesses two of the most fundamental ingredients for life: liquid water and organic chemistry. But to understand how life could exist on a world like this, we need to embrace a fascinating new idea: the Haitian planet. Imagine a world that is nothing like Earth. A Haitian planet, a portmanteau of hydrogen and ocean, is a hypothetical type of planet with a massive, hydrogen-rich atmosphere surrounding a global, planet-wide ocean. There is no land, no continents, just an endless, deep sea that could span the entire globe. On such a world, the surface would be incredibly hot due to a strong greenhouse effect from the thick hydrogen atmosphere. Temperatures could soar to levels that would be intolerable for complex life. However, and this is the critical part, as you descend beneath the atmosphere and into the depths of that global ocean, the pressure and temperature could create a layer, a sweet spot where conditions are just right for liquid water to exist. Life wouldn't thrive on the surface. It would exist in the dark, hidden depths, completely isolated from the star above. This is the compelling possibility for K2-18b. While its surface is likely a scorching hothouse, beneath the dense atmospheric shroud could lie a vast, warm ocean. In such an environment, life wouldn't rely on sunlight for energy, just as life around hydrothermal vents in Earth's deepest oceans doesn't. Instead, it could derive energy from chemical reactions, a process known as chemosynthesis. The detection of methane is particularly intriguing here, as on Earth, a significant portion of methane in our atmosphere is produced by biological sources. While it can also be produced by geological activity, its presence alongside water vapor and carbon dioxide makes for a tantalizing, albeit inconclusive, chemical cocktail. K2-18b demonstrates that the search for life must extend beyond looking for a second Earth. We must now seriously consider the potential for entire biospheres to exist in the global oceans of these enigmatic water worlds, proving that the universe's creativity in crafting potential habitats for life far exceeds our own imagination. Now we turn our attention to a world that holds a unique and quiet promise, orbiting one of the smallest and most peaceful stars we have ever discovered. Tigodon's star, a faint red dwarf located just 12 light-years away, is a stellar senior citizen, an ancient beacon that has been burning for at least 8 billion years, far longer than our own sun. This remarkable age is a gift of time, and around it, astronomers have found two Earth-sized planets, with Teegarden Star B emerging as a particularly compelling candidate. What makes this planet so extraordinary is its Earth Similarity Index, a measure used by scientists to compare exoplanets to our own world. On this scale, Teegarden B scores remarkably high, not because it looks like Earth, but because its mass is almost identical to our planet's. It is one of the closest matches to Earth's mass we have ever found orbiting within a habitable zone. The profound advantage of Teegarden Star B lies entirely with its parent star. Unlike the volatile, flare-prone red dwarfs we've encountered, Teegarden Star is exceptionally calm and stable. It emits a gentle, steady glow with very little of the violent magnetic activity that can ravage younger, more turbulent stars. For a planet like Teegarden B, which orbits very close to its dim sun, this tranquility is everything. It means the planet has likely been spared the apocalyptic stellar storms that could have stripped away its atmosphere eons ago. Instead, it has enjoyed billions of years of quiet, consistent warmth. This opens up the possibility of a stable climate existing over geological timescales, a luxury that even Earth, with its ice ages and warming periods, has not consistently experienced. Such long-term stability is considered a crucial ingredient for the slow, gradual process of life's emergence and evolution from simple chemistry to complex biology. Imagine the surface of such a world. Tidally locked, one hemisphere would forever face the faint, dark crimson orb of its star, while the other would be turned to the eternal blackness of space. But with a stable atmosphere, winds could circulate heat from the day side to the night side, potentially creating a vast, temperate twilight band where conditions are just right. The sheer age of this system is what sparks the deepest curiosity. Life on Earth took nearly 1 billion years to get started and billions more to reach complexity. Teegarden Star B has had more than twice as long as Earth for those same processes to begin. If life did arise there, it has had an almost unimaginable head start. What forms might it have taken? This ancient, quiet world forces us to consider that the most advanced life in our cosmic neighborhood might not be on a planet like ours, orbiting a star like our Sun, but on a world forever bathed in the deep red light of a silent, ancient dwarf, a testament to the patient, slow-burning potential of the universe. While its sibling, Teegarden Star B, may enjoy a more temperate position, the other planet in this ancient system presents a very different, yet equally fascinating set of possibilities. Teegarden Star C orbits a bit farther out from its faint sun, receiving significantly less stellar energy. This places it on the cold, outer fringe of the system's habitable zone. If Teegarden B is analogous to a cozy spot near a small fireplace, then Teegarden C is like a room at the far end of the hall where the warmth barely reaches. At first glance, this might seem to relegate it to the status of a frozen wasteland, a world locked in a perpetual global ice age. But in our search for life, we have learned that a cold exterior can often hide a warm heart, and this is where the story of Teegarden C becomes truly intriguing. The key question for this colder world is the nature of its surface. If it has a thin atmosphere, it is almost certainly a frozen ball of rock and ice. However, if it possesses a thick atmosphere rich in greenhouse gases like carbon dioxide or methane, that gaseous blanket could trap enough of the star's feeble heat to create surface temperatures above freezing, at least in some regions. This scenario would make it a candidate for a more conventional, though undoubtedly chilly, habitable world. The other, and perhaps more compelling, possibility is that Teegarden C is an ice-covered world with a vast global ocean hidden beneath a thick, frozen crust. This concept is not science fiction. We have a perfect example right here in our solar system, Jupiter's moon Europa. Europa is far outside our Sun's habitable zone and receives almost no warmth from the Sun, yet it is considered one of the most promising places to find life because it harbors a salty liquid ocean beneath its icy shell. What keeps Europa's ocean from freezing solid is not solar energy, but internal heat generated by gravitational tidal forces. As Europa orbits the massive planet Jupiter, the immense gravitational pull flexes and stretches the Moon's interior, creating friction and heat. This process, known as tidal heating, is so effective that it can maintain a liquid water ocean possibly dozens of kilometers deep. For Teegardens star C, a similar mechanism could be at work. Even though its star is small, the planet could be experiencing tidal heating from the gravitational interactions with its sibling planet, Teegardens B, or from the star itself if its orbit is not a perfect circle. This internal warmth could be enough to sustain a subsurface ocean completely isolated from the cold, dark surface above. This transforms our view of habitability. Life on such a world would not exist on the surface under a crimson sky. It would thrive in a sunless abyss, a dark ocean potentially warmed by hydrothermal vents on the seafloor. On Earth, we find entire ecosystems thriving in the absolute darkness of the deep ocean, powered not by photosynthesis but by chemosynthesis, where microbes convert chemicals from volcanic vents into energy. A subsurface ocean on Teegardens C could provide a stable, protected environment for billions of years, safe from any potential stellar flares and the harsh conditions of space. The idea that the two planets in the Teegardens system could represent two vastly different models of habitability, one a potentially temperate surface world and the other a life-bearing water world hidden under ice, is a powerful reminder of the diversity of environments where life could gain a foothold. This ancient, quiet solar system may not just hold one, but two profound secrets about the potential for life in the cosmos. Now, let's venture into a stellar configuration that sounds like it's straight out of a science fiction epic, a planet with not one, not two, but three suns in its sky. This is JJ667cc, a super-Earth that challenges our single-star perspective on habitability and opens up a realm of celestial possibilities. Located a relatively close 22 light-years away, this planet orbits the smallest member of a triple star system, a red dwarf known as JJ667c. The planet itself is a substantial world with a mass more than 3.5 times that of Earth, placing it firmly in the super-Earth category and suggesting a rocky, if more massive, composition. Its most critical feature is its orbit right in the middle of its star's habitable zone, completing a year in just 28 Earth days as it circles its dim crimson sun. The true wonder of JJ667cc, however, lies in its complex cosmic ballet. The red dwarf it orbits is itself gravitationally bound to a pair of larger, brighter stars, JJ667 A and B. From the surface of this distant world, its primary sun would appear as a large, deep red orb. But the other two stars would also be visible, shining in the sky like a pair of incredibly brilliant, piercingly white stars, thousands of times brighter than our full moon. They would be close enough together to appear as a single, dazzling double star to the naked eye. This creates a lighting scenario unlike anything we can experience on Earth. For most of its short orbit, the planet is illuminated by its primary red sun, casting a perpetual sunset hue across the landscape. But there would be times, depending on the alignment of the stars, when the light from the brighter, hotter companion stars would add their intense, white-blue light to the mix, creating periods of combined illumination that could dramatically alter the planet's surface conditions in a rhythmic, celestial dance. This multi-star environment forces us to rethink the very basics of how life might function. Consider the process of photosynthesis, the way plants on Earth convert sunlight into energy. Our plants are optimized for the specific spectrum of light emitted by our yellow sun. On JJ667cc, the dominant light source is from a red dwarf, which emits most of its energy in the infrared and red part of the spectrum. Any potential life forms would have had to evolve photosynthetic pigments that are efficient at absorbing these red wavelengths. But then, during the periods when the brighter companion stars add their light, the planet would be bathed in a surge of blue-white light similar to that of our own Sun. This could lead to a bizarre and fascinating possibility, a biosphere that operates on two different photosynthetic systems, one for the long, steady red light periods and another that kicks in during the intense, brief bursts of blue light. Life there might have evolved to be highly adaptable, switching its metabolic processes based on the changing skies above. The discovery of JJ667cc itself is a testament to the ingenuity of astronomers. It was found not by the transit method, where a planet passes in front of its star, but by the radial velocity method. This technique detects the tiny wobble a planet's gravity induces in its host star, a subtle tug that reveals the planet's presence and mass. Detecting a planet as small as JJ667cc in a multi-star system was a monumental achievement, as the gravitational influences of the other stars create a complex background signal that had to be meticulously untangled. Its confirmation solidified its status as a prime candidate for future study. The potential for a thick atmosphere on a world of this mass, combined with its complex stellar environment, makes it a high-priority target for next-generation telescopes. Analyzing the light filtering through its air could reveal how such an atmosphere responds to the varied light of three different suns, offering a Chinese letter GLIMPSE into one of the most exotic and potentially habitable environments we have yet discovered in our galactic neighborhood. Moving from the triple-star spectacle of JJ667cc, we find that red dwarf systems continue to surprise us with their sheer variety, even when they host just a single star. Our next two destinations, JJ357d and JJ1061c, may orbit different suns, but they perfectly illustrate the dramatic range of conditions that can exist within the loosely defined boundaries of a habitable zone. These two worlds, while both promising, represent almost opposite ends of the spectrum, showing us that a planet's position relative to its star is just the beginning of the story. Let's start with JJ357d, a super-Earth located 31 light-years away. This planet is a fascinating puzzle. It's about 6 times more massive than Earth, which places it right on the cusp between a massive rocky planet and a mini Neptune. Its true nature remains one of its biggest mysteries, but what truly sets JJ357d apart is its orbit. This world is far from its dim red sun, with a year lasting about 55 Earth days. Because the star is so faint, this distant orbit still places the planet within the theoretical habitable zone. However, the amount of stellar energy it receives is remarkably low, comparable to what Mars gets from our Sun. This immediately raises a critical question: could a world this cold and distant ever be habitable? The answer depends almost entirely on the planet's atmosphere. If JJ357d is a bare rock with a thin or non-existent atmosphere, it would be a deeply frozen world, far too cold for liquid water to exist on its surface. But if it possesses a thick, hydrogen-rich atmosphere, it could experience a powerful greenhouse effect. In this scenario, the atmosphere would act like an incredibly effective insulating blanket, trapping what little heat it receives from its star and potentially raising surface temperatures to levels where water could remain liquid. This is the mini Neptune possibility, a world with no true surface but perhaps a deep, warm ocean beneath a dense gaseous shroud. Alternatively, if it is a rocky super-Earth with an atmosphere rich in greenhouse gases like carbon dioxide, it could also achieve temperate conditions. JJ357d teaches us that the outer edge of the habitable zone is not a fixed line, but a frontier that can be pushed outward by the unique properties of a planet's air, challenging our simple definitions of what makes a world just right. In stark contrast to this distant, chilly world, we have JJ1061c. This planet is part of a compact system just 12 light-years away, a family of at least 3 planets all very close to Earth's mass. While GJ 357d explores the cold outer frontier, GJ 1061c sits perilously close to the inner edge of its star's habitable zone. It's a world on a tightrope. It receives significantly more stellar energy than Earth, placing it in a position where the risk of a runaway greenhouse effect is very real. This is the fate that befell Venus in our own solar system, a planet that started with water but saw its temperatures soar until its oceans boiled away, leaving a scorching, acidic atmosphere behind. The potential environments of these two worlds could not be more different. GJ 357d might be a cold, potentially icy world whose habitability is entirely dependent on a supercharged atmospheric greenhouse. GJ 1061c, on the other hand, could be a warmer, perhaps even tropical planet, where the constant influx of energy from its star creates a vastly different climate. The key to its survival as a habitable world is the same as for its distant cousin, the atmosphere. A moderate atmosphere with the right balance of gases could allow GJ 1061c to maintain comfortable temperatures, perhaps with large, warm oceans. But a slightly thicker atmosphere could tip it over the edge into a Venus-like hellscape. What makes this planet especially intriguing is its membership in a tightly packed system. The planets of GJ 1061 are so close together that, much like in the TRAPPIST-1 system, the idea of material and even potential life being exchanged between them is a compelling possibility. GJ 1061c demonstrates that the inner edge of the habitable zone is a precarious place, a delicate balancing act between a temperate water world and a dry, uninhabitable oven. Together, these two planets show that the concept of a habitable zone is not a single, uniform region, but a broad and diverse band where a planet's atmosphere, mass, and geological history ultimately write its final story. Moving from the delicate balancing act of GJ 1061c, we find another nearby world that exemplifies the precarious nature of life on the inner edge of a red dwarf's habitable zone. Just 14 light-years away, practically a stone's throw in galactic terms, orbits a super-Earth known as Wolf 1061c. This proximity makes it one of the closest known potentially habitable exoplanets to Earth, a neighbor whose secrets we are intensely eager to unravel. With a mass a little over 4 times that of our own planet, Wolf 1061c is a substantial world, likely possessing a rocky surface and gravity that would feel noticeably stronger to any visitor. But the most defining characteristic of this world is the frantic pace of its existence. Due to its incredibly tight orbit around its cool M-dwarf star, a single year on Wolf 1061c, one complete trip around its sun flies by in a mere 18 Earth days. This close proximity comes with a suite of formidable challenges that we are beginning to recognize as common yet critical hurdles for life in red dwarf systems. The first is the high probability of tidal locking. Just as our moon always shows the same face to Earth, Wolf 1061c is almost certainly locked, with one hemisphere perpetually baked in the harsh, reddish light of its star, while the other is frozen in the absolute darkness and cold of space. The day side would be scorching, the night side an icy tomb, creating two utterly hostile environments. Compounding this is the nature of its parent star. Like many M-dwarfs, Wolf 1061 is prone to flares, sudden, violent eruptions that blast the planet with intense X-ray and ultraviolet radiation. Without significant protection, such stellar tantrums could have, over eons, stripped away any primordial atmosphere and bathed the surface in radiation levels inimical to life as we know it. Yet, despite these daunting obstacles, Wolf 1061c remains a compelling candidate, and the reason lies in the potential power of a planetary atmosphere. An atmosphere is far more than just air to breathe. It is a dynamic engine for transporting heat and a protective shield against radiation. If Wolf 1061c has managed to hold onto a thick enough atmosphere, it could fundamentally rewrite its story. Winds and weather patterns could act as a global heating and cooling system, circulating warm air from the permanent day side to the frigid night side and pulling cold air back in return. This constant atmospheric churning would prevent the most extreme temperature differences from taking hold. Instead of a sharp divide between a blazing desert and a frozen wasteland, the entire planet could be wrapped in a more temperate, if unusual, climate. The most likely region for habitability in such a scenario would be the Terminator line, the narrow twilight band that circles the planet, forever marking the boundary between day and night. Here, the conditions could be remarkably stable. It would be a land of eternal sunrise or sunset, with the star permanently sitting on the horizon, casting long, deep red shadows. In this twilight zone, temperatures moderated by the global air currents could be comfortable enough for liquid water to persist on the surface. This would create a bizarre, ribbon-like world where life, if it exists, would be confined to a thin band of land, never experiencing the height of day or the depth of night. The survival of this environment would be a constant battle, dependent on the atmosphere's ability to withstand the star's flares and maintain its protective circulation. Wolf 1061c stands as a testament to the idea that a planet's potential is not defined by its position alone, but by the complex interplay between its star, its orbit, and the life-sustaining blanket of air it may or may not possess. After exploring the dynamic but challenging worlds around red dwarf stars, we now arrive at a destination that feels strikingly familiar, a world that has earned the nickname Earth's cousin for very good reasons. Kepler 452b represents a milestone in our search because for the first time we found a planet that isn't just similar to Earth in one or two ways, but in several key aspects at once. It orbits a star classified as a G-type dwarf, the same type of star as our Sun. This sun, Kepler 452, is only about 10% larger and 20% brighter than our own, making it the most Sun-like star known to host a potentially habitable Earth-sized world. The planet itself is about 60% larger than Earth, placing it in the super-Earth category, but its orbital period of 385 days is remarkably close to our own 365-day year. It resides comfortably within its star's habitable zone, receiving just a bit more energy from its sun than Earth does from ours. This combination of factors is what makes Kepler 452b so significant. While many of the promising worlds we've discussed orbit small, fiery red dwarfs, this planet shows us that planetary systems resembling our own do indeed form around sun-like stars. It confirms that the architecture of our solar system is not a cosmic oddity. For scientists hoping to find a true Earth analog, a world with a similar day-night cycle, a stable stellar parent, and a comparable energy budget, Kepler 452b is the closest match we have discovered to date. It allows us to move beyond hypotheticals and ask more concrete questions about how life might develop under conditions that, at least on paper, appear so similar to those on our own planet. However, this compelling familiarity comes with a profound and sobering twist. The Kepler 452 system is ancient. It is estimated to be about 6 billion years old, which makes it roughly 1.5 billion years older than our own solar system. This immense age difference is not just a number, it represents a vast chasm of time with dramatic implications for the planet's history. Think about what Earth has accomplished in its 4.5 billion years. Life emerged, evolved from single-celled organisms into complex animals, and eventually gave rise to a technological civilization. Kepler 452b has had an extra 1.5 billion years for its story to unfold. If life did arise on this world, it has had an almost unimaginable head start. This leads to two fascinating yet equally daunting possibilities. The first is a vision of unparalleled advancement. A biosphere with an additional 1.5 billion years of evolution could have produced life forms of staggering complexity and intelligence. The planet could be home to a civilization so ancient and technologically sophisticated that its achievements would be beyond our comprehension. Alternatively, that vast expanse of time could also point toward a more somber fate. A planet older than Earth has had more time to exhaust its resources or succumb to existential threats. The increased energy output from its aging star, which is gradually growing brighter, might have already triggered a runaway greenhouse effect. Kepler 452b could be a vision of Earth's distant future, a once lush world that has become a scorched and barren desert, its oceans long since evaporated. The quiet, enduring light from this ancient system holds a secret that is both thrilling and cautionary, offering us a glimpse of a path our own world might one day follow. Just when we thought the treasure trove of data from the Kepler mission had been fully mined, astronomers made a discovery that proves the value of looking back with fresh eyes. Kepler 1649c is a world that was hiding in plain sight, overlooked by automated computer algorithms during the initial analysis of the Kepler data. It took a dedicated team of citizen scientists, volunteers combing through the data by hand, to spot the subtle signal of this remarkable planet, a testament to human intuition and perseverance in the age of machine learning. And what they found was worth the extra effort, arguably the most Earth-like exoplanet ever discovered in terms of its size and the energy it receives from its star. The numbers for Kepler 1649c are astonishingly familiar. This planet is located about 300 light-years away and orbits a red dwarf star. But unlike many of the super-Earths we've discussed, Kepler 1649c is a true Earth twin in scale, with a radius almost identical to our own planet. Even more compelling is its position in the habitable zone. It receives about 75% of the stellar energy that Earth gets from the Sun. This places it in a similar situation to Mars in our solar system in terms of sunlight, but with one critical difference. Mars is a small planet that lost its atmosphere, while Kepler 1649c, being Earth-sized, has a much better chance of holding onto a substantial atmosphere that could trap that heat effectively. With a thick atmosphere containing greenhouse gases, this world could easily maintain temperatures suitable for liquid water on its surface, making it one of the best candidates we have for a temperate, Earth-like environment. What truly sets this discovery apart is the profound lesson it teaches us about our own search. The fact that such a promising world was initially missed by algorithms reminds us that our methods are not infallible and that the universe still holds secrets that can only be revealed through careful, human-driven scrutiny. It suggests that if a planet this similar to Earth was overlooked in a relatively small sample of stars, then the actual number of such worlds in our galaxy could be even higher than our most optimistic estimates. Kepler 1649c is a powerful symbol of potential abundance, a hint that planets with the basic ingredients for life might be commonplace, waiting to be found not just in new data, but in the archives we have already collected. This discovery reinvigorates the entire field, suggesting that the cosmic census of habitable worlds is far from complete and that our closest twin might still be out there, its signal buried in the starlight, just waiting for the right pair of eyes to find it. Shifting our focus from the Kepler legacy, we turn to the next generation of planet hunting and a remarkable system discovered by NASA, a transiting exoplanet survey satellite, or TESS. The TOI 700 system, located just over 100 light-years away, has quickly become a showcase for the incredible potential of this new mission. Here, orbiting a quiet and stable M-dwarf star, we find not one, but a family of small, rocky worlds with TOI 700d, E, and F offering a masterclass in comparative planetology. The true beauty of this system lies in the subtle differences between these sibling planets. allowing scientists to study how small variations in orbit and stellar energy can lead to dramatically different planetary environments. The first major discovery here was TOI 700d, an Earth-sized planet that captured headlines as the first of its size found by TESS to be orbiting within its star's habitable zone. This world, a bit larger than our own, completes an orbit every 37 days. Its position suggests it receives about 86% of the stellar energy that Earth gets from the Sun, a figure that places it in a comfortably temperate position within the Goldilocks zone. But the story became even richer with the subsequent discovery of TOI 700e. This planet, also Earth-sized, orbits even closer to the star, with a year lasting just 28 days. It resides in what scientists call the optimistic habitable zone, a region where the possibility for liquid water exists under certain atmospheric conditions, though it might be on the warmer inner edge. Finding two Earth-sized worlds in the same system, both within the broader boundaries where life could potentially arise, was a monumental achievement that immediately elevated the importance of TOI 700. Then there is TOI 700f, the innermost known planet in the system. Its status is less certain. It's smaller and on a very tight 8-day orbit, placing it almost certainly outside any conventional definition of the habitable zone. While it is likely far too hot for life as we know it, its presence completes the picture of this compact planetary family. The existence of TOI 700f gives us crucial information about the system's architecture and formation history, helping us understand how these worlds came to be arranged as they are. It acts as a control subject of sorts, a stark reminder of the harsh conditions that define the inner boundary of a star's life-friendly region. The profound significance of the TOI 700 system is not just about the individual planets, but about the opportunity they present as a group. This is the power of comparative planetology. Imagine being able to study three worlds, all formed from the same raw materials around the same star, yet each occupying a slightly different orbital position. With instruments like the James Webb Space Telescope, astronomers can now aim to analyze the atmospheres of both TOI 700d and TOI 700e. By comparing them, we can answer fundamental questions. Does the outer planet, TOI 700d, have a thicker atmosphere because it formed in a cooler region where volatile gases could more easily condense? Has the inner planet, TOI 700e, lost its atmosphere to the more intense radiation from its star, or does it possess a different chemical composition altogether? This side-by-side comparison is like having a controlled laboratory experiment on a cosmic scale. It allows us to move beyond studying single, isolated worlds and begin to understand the rules that govern planetary evolution and habitability across an entire system. The TOI 700 planets offer a unique window into how common Earth-like conditions might be, not as singular accidents, but as predictable outcomes in the right stellar environment. Leaving the compact red dwarf systems behind, we now arrive at a world that offers a glimpse into a more sun-like and perhaps more familiar kind of stellar neighborhood. About 42 light-years away in the constellation Pictor orbits a planet known as HD 40307G. This super-Earth is part of a fascinating multi-planet system that initially surprised astronomers. The star HD 40307 is a K-type orange dwarf, a category we've seen is often more stable and long-lived than our own Sun. When the system was first discovered, it was thought to contain 3 super-Earths, all orbiting so close to their star that their surfaces would be scorched. But then, with more refined data analysis, a remarkable fourth world was found, pushed out into a much wider orbit. That planet is HD 40307G, and its discovery completely changed our understanding of this distant solar system. What makes this world so promising is its newfound position. HD 40307G orbits its star at a distance that places it squarely within the habitable zone. Its year lasts about 200 Earth days, and it receives a level of stellar energy from its K-type sun that is remarkably similar to what Earth receives from our G-type sun. This is a significant departure from the faint red suns that dominate our list. An orange dwarf provides a brighter, whiter light, much closer in quality to the daylight we experience here. For any potential life on the surface, this means the conditions for processes like photosynthesis would be far more analogous to those on Earth. The star is also exceptionally stable, with very low levels of the magnetic activity that causes the destructive flares common to smaller red dwarfs. This offers HD 40307G a much calmer and more consistent environment in which to develop over billions of years. As a super-Earth with a mass at least 7 times that of our planet, the central question about HD 40307G is its true nature. Is it a massive, rocky world with a solid surface, or has it crossed the threshold into becoming a mini Neptune, a world shrouded in a thick, gaseous envelope? The current evidence leans intriguingly toward the former. Its calculated density suggests it is likely a terrestrial planet, a mega-Earth with a solid surface you could theoretically stand on, though the gravity would be considerably stronger. This possibility of a rocky world, combined with its ideal location in the habitable zone of a stable, sun-like star, makes it one of the most compelling candidates for a truly Earth-like environment, albeit on a larger scale. The climate on such a world could be complex and dynamic, with the potential for liquid water oceans and an atmosphere capable of supporting a rich and varied biosphere. The story of HD 40307G is a powerful reminder that our search must extend beyond single, isolated planets to understand the full architecture of a system, as a world that was once hidden in the data can turn out to be the most promising of all. Now we journey to a world that is not just old, but truly ancient, a relic from the earliest days of our galaxy. Located a mere 13 light-years away, a distance that makes it one of our closest stellar neighbors, Captain B is a super-Earth that offers a profound glimpse into a past so distant it challenges our understanding of cosmic time. The planet itself is massive, weighing in at nearly 5 times the mass of Earth, but its true significance lies not in its size, but in the incredible age of its parent star. Captain Star is a dim red dwarf, but it is no ordinary star. It belongs to a rare population known as the galactic halo, a vast, spherical cloud of ancient stars that surrounds the main disk of the Milky Way. This star is a fugitive, moving in a highly elliptical, retrograde orbit around the galactic center at tremendous speed. Astronomers believe it was likely ripped away from a dwarf galaxy that was devoured by the Milky Way in a violent merger event billions of years ago. The consequence of this dramatic history is an almost incomprehensible age. Captain Star is estimated to be around 11.5 billion years old. That means it formed when the universe itself was just 2 billion years old, making this system more than twice as old as our Sun and Earth. Captain B orbits within the habitable zone of this ancient star, and this fact leads to a staggering possibility. If this planet has been habitable for even a fraction of its existence, it means the conditions for life could have arisen there up to 8 billion years before life even began on our own world. 8 billion years is an epoch of time so vast it defies human imagination. To put it in perspective, the entire history of complex life on Earth, from the first multicellular organisms to the rise of humanity, spans less than 1 billion years. Captain B has had 8 times that long for its story to unfold. This forces us to confront a truly mind-boggling question: what could life become with such an unimaginable head start? On Earth, evolution is a process of slow, gradual change punctuated by mass extinctions and environmental shifts. But on a stable world with an incredibly ancient biosphere, evolution would have had billions of additional years to experiment, to refine, to complexify. The potential for life forms of staggering sophistication and intelligence is not just plausible, it could be the inevitable outcome of such deep time. The environment of Captain B, however, would be fundamentally different from Earth's, shaped by its unique galactic surroundings. Because it orbits a halo star, its journey through the galaxy is a solitary one, far from the rich, star-filled spiral arms where new stars are constantly being born. Its sky would be darker, with fewer nearby stars, and it would have witnessed a much younger, more turbulent galaxy in its youth, one filled with higher levels of radiation from frequent supernova explosions. Could life have not only begun in such an environment but also persisted through these early cosmic trials? If it did, the life that evolved would be shaped by these conditions. It might possess incredibly robust biological repair mechanisms to handle higher background radiation, or its entire biochemistry might be based on a foundation far hardier than our own. The very concept of a civilization on Captain B is humbling. A technological society with a history stretching back millions or even billions of years would view the universe in ways we cannot begin to fathom. Their knowledge of cosmology, physics, and the nature of reality itself would be so advanced that our own science might appear as mere child's play. Captain B stands as a silent, ancient monument to the potential for life in the cosmos, a reminder that our own timeline on Earth may be just a brief, opening chapter in a story that has been unfolding for nearly the entire age of the universe. Our journey through the cosmos now brings us to a world that may or may not be there at all, a planet whose very existence has been one of the most debated topics in modern astronomy. This is the story of JJ581G, a potential super-Earth whose discovery was announced with great excitement, only to be plunged into a controversy that highlights the intricate challenges of finding new worlds light years away. Located a relatively close 20 light-years from Earth, the JJ581 system was already known to host several planets, but the announcement of Planet G was different. Initial analyses of the data suggested this world was not only real but positioned perfectly within the star's habitable zone, a rocky world with a mass just 3 to 4 times that of Earth, orbiting its quiet red dwarf sun in a mere 37 days. For a moment, it seemed we had found one of the strongest candidates for a habitable world right in our stellar backyard. The method used to detect JJ581G is key to understanding the dispute. It was found using the radial velocity technique, which does not involve watching the planet pass in front of its star. Instead, incredibly precise instruments measure the tiny wobble a planet's gravity induces in its host star. It's like trying to detect a slight, rhythmic tug on a star from billions of kilometers away. The signal for JJ581G was exceptionally faint, buried within the complex gravitational pulls of the other known planets in the system. One team of astronomers, after years of painstaking data collection, believed they had successfully separated this subtle signal from the noise, pointing to the existence of a world in the life-friendly zone. The potential implications were enormous, suggesting a planet with the right conditions for liquid water. However, science thrives on skepticism and independent verification. When other research groups attempted to reanalyze the exact same dataset, they reached a very different conclusion. They argued that the proposed signal for Planet G was not caused by a planet's gravity at all, but was actually an artifact of the star's own activity. Red dwarf stars like JJ581 have complex magnetic cycles and starspots, dark, cooler regions on their surface that can mimic the subtle wobble of an orbiting planet. The controversy over JJ581G is not a story of error, but a testament to the cutting-edge difficulty of this work. It represents the very frontier of our detection capabilities, where the signal of a planet is so faint that it brushes up against the inherent noise and variability of the star itself. This ongoing debate offers a powerful, real-time lesson in how scientific understanding evolves. It shows the rigorous process of claim and counterclaim that is essential for building reliable knowledge. The case of GJ581G forces us to confront the fact that our view of the cosmos is not always clear. It is a picture we are slowly piecing together, one data point at a time, and sometimes those pieces can be interpreted in more than one way. Whether this specific world is ultimately confirmed or dismissed is almost secondary to the profound insight it provides. It reminds us that every new planet discovery is a hard-won victory against immense technical challenges, and that our map of potentially habitable worlds is a living document, constantly being revised and refined as our tools and techniques improve. The unresolved mystery of GJ581G underscores a thrilling reality. Even in a field driven by data and precision, there is still room for discovery and debate at the very edge of what is possible. Shifting our focus from the unresolved mystery of GJ581G, we arrive at a world where the conditions for life hinge on a seemingly simple, yet remarkably complex planetary feature: clouds. HD 85512b is a super-Earth orbiting a K-type orange dwarf star about 37 light-years away. This planet, with a mass roughly 3.5 times that of Earth, sits in a precarious and fascinating position. It lives on the very inner edge of its star's habitable zone, a place where the line between a temperate water world and a scorching Venus-like hellscape is incredibly thin. What makes this world a compelling case study is not just where it is, but what it might need to possess in order to be habitable: a very specific type of global weather system. Planetary climate models are sophisticated computer simulations that scientists use to predict the conditions on distant worlds based on factors like their mass, distance from their star, and the hypothetical composition of their atmosphere. When researchers applied these models to HD 85512b, they discovered its potential for life is critically dependent on its ability to reflect a significant amount of its star's energy back into space. This is where clouds enter the picture. The models suggest that for this planet to maintain a comfortable surface temperature suitable for liquid water, it would need a cloud cover of at least 50%. These wouldn't be just any clouds, they would need to be highly reflective, composed of water droplets, much like the bright, puffy cumulus clouds we see on Earth. These clouds would act as a planetary sunshade, bouncing a large portion of the incoming stellar radiation away before it can heat the surface and trigger a runaway greenhouse effect. This introduces us to the concept of planetary albedo, which is essentially a measure of how reflective a world is. A planet with a high albedo, like an ice-covered world, reflects most sunlight and stays cool. A planet with a low albedo, like a dark ocean or a rocky surface, absorbs most sunlight and heats up. For HD 85512b, the right amount of cloud cover provides a natural thermostat. If the planet starts to get too warm, more water would evaporate from its oceans, potentially forming more clouds, which would then reflect more sunlight and cool the planet down. This negative feedback loop is a key stabilizing force in Earth's own climate, and its potential existence on another world is a thrilling prospect. It transforms the question of habitability from a simple matter of location to a dynamic interplay between a planet's atmosphere, its hydrosphere, and even its biology, as life itself can influence cloud formation. The fine balance required for HD 85512b underscores just how delicate the recipe for a habitable world can be. If the cloud cover were to drop below that critical 50% threshold, the delicate equilibrium would shatter. More sunlight would be absorbed, temperatures would rise, leading to more ocean evaporation. But in this scenario, if the atmosphere becomes too saturated with water vapor, a potent greenhouse gas itself, it could trap heat more efficiently, leading to even higher temperatures and more evaporation in a devastating positive feedback loop. This is the pathway to a runaway greenhouse effect, the very process that likely turned Venus from a potentially watery world into the inferno it is today. So, the story of HD 85512b is a tale of two possible futures, one where a protective blanket of clouds fosters a stable climate, and another where their absence leads to a planetary oven. It serves as a powerful reminder that being in the habitable zone is not a guarantee of habitability. It is merely an invitation, and the final outcome depends on a world's specific and often fragile set of characteristics. Returning to the foundational discoveries that reshaped our entire field, we encounter a world that served as a beacon of hope and a catalyst for the modern age of exoplanet science. Kepler 22b holds a special place in the history of our search, not necessarily for what we know about it, but for what its discovery represented. Imagine the year 2011. The Kepler Space Telescope was still in its prime, diligently monitoring the brightness of over 100,000 stars, and the scientific community was holding its breath, waiting for that first definitive signal. Then it came, the announcement of Kepler 22b, the very first planet the mission had confirmed to be orbiting squarely within the habitable zone of a star remarkably similar to our own Sun. This was not just another data point, it was a validation of the entire endeavor, a moment that transformed the hunt for other Earths from a speculative dream into a tangible, achievable goal. The statistics of Kepler 22b were immediately captivating. Located about 600 light-years away, this planet orbits a G-type star, a close cousin to our Sun, completing a year in 290 Earth days. Its position within the habitable zone was perfect, receiving about 85% of the stellar energy that Earth gets, suggesting that if it had a similar atmosphere, its surface temperatures could be remarkably temperate. The initial wave of excitement was palpable. News outlets and scientists alike heralded it as a potential Earth 2.0. The public imagination soared with visions of a blue and green marble swimming in the distant black, a world that could be brimming with oceans, continents, and perhaps even life. It was a moment of pure, unadulterated optimism, a proof of concept that the telescope was working exactly as intended, and that planets in the life-friendly zone around Sun-like stars were not just theoretical but real and detectable. However, as more data was analyzed, a more nuanced picture of Kepler 22b began to emerge, teaching us one of the most important early lessons in exoplanetology. Location is only part of the story. The planet's radius was measured to be about 2.4 times that of Earth. This size placed it squarely in a mysterious category that we now frequently encounter. It could be a massive rocky super-Earth, but it is just as likely, if not more so, to be a mini-Neptune. A mini-Neptune has no solid surface to speak of. Instead, it would possess a deep, thick atmosphere of hydrogen and helium, possibly covering a mantle of high-pressure water, ammonia, or other ices, and a small rocky core. A visitor to such a world would find no ground to stand on, only an endless, crushing gaseous envelope that grows denser and hotter with depth until any notion of a familiar environment is lost. This fundamental uncertainty about Kepler 22b's true nature does not diminish its importance. In fact, it enhances it. The planet became a living lesson in the complexity of our search. It showed us that simply finding a world of roughly the right size in the habitable zone is just the first step. The subsequent, more difficult work involves characterizing its atmosphere, density, and composition to understand what kind of world it truly is. Kepler 22b forced astronomers to ask deeper questions and develop more sophisticated models. Could a mini-Neptune even be habitable? Perhaps, if it hosted a deep, global ocean beneath its atmosphere where pressures and temperatures created a layer suitable for liquid water, a concept we now explore for worlds like K2-18b. But it would be an alien habitat, nothing like the Earth-like environment we initially envisioned. The legacy of Kepler 22b, therefore, is twofold. First, it was the crucial proof that ignited the field. demonstrating the power of the transit method and giving us the confidence that we were on the right track. It paved the way for the thousands of exoplanet discoveries that followed, each one building on the techniques and optimism generated by this pioneering world. Second, and just as importantly, it was our introduction to the humbling reality that the universe creates a stunning diversity of planets. Not every world in the habitable zone will be a twin of Earth. Some will be water worlds, some gaseous, some icy. Kepler 22b broadened our definition of habitable and set the stage for the more nuanced, complex, and ultimately far more interesting search we are engaged in today. It remains a symbol of a pivotal turning point, a world that opened a door and showed us that the cosmic landscape was far richer and more varied than we had ever dared to imagine. As we reflect on the monumental legacy of the Kepler Space Telescope, we can look to two specific discoveries that perfectly encapsulate the mission's enduring contribution to our cosmic perspective. Consider Kepler 1638b, a super-Earth situated roughly 2,300 light-years away. This world is notable for the star it calls home, a G-type star that is a near twin to our own Sun. Finding a planet of this size, over 50% larger than Earth, orbiting comfortably within the habitable zone of a Sun-like star was a key piece of the puzzle. It confirmed that the architecture of our own solar system, with rocky worlds at temperate distances from a stable yellow star, is not a singular fluke but a template that nature repeats. The existence of Kepler 1638b suggests that countless stars similar to ours could be hosting families of planets, some of which may have conditions analogous to those that nurtured life on our own world. In stark contrast to this familiar setting, we have Kepler 1229b, located about 770 light-years distant. This planet is a prime example of the other major category of habitable zone worlds we've discovered. It is much closer to Earth in size, but it orbits a very different kind of star, a red dwarf. Its environment would be one of perpetual, deep crimson light, a landscape forever bathed in the glow of its cool, dim sun. The fact that Kepler found an Earth-sized planet in the habitable zone of such a common star type was equally, if not more, significant. It demonstrated that the potential for life is not confined to solar systems that look like our own. The conditions for liquid water can arise around the smallest, most numerous stars in the galaxy, drastically expanding the number of possible addresses for biology in the cosmos. Together, Kepler 1638b and Kepler 1229b represent the two dominant pathways to potential habitability that the Kepler mission revealed. One path leads to worlds orbiting stars like our Sun, offering a kind of familiarity that resonates with our own experience. The other path leads to the more exotic and far more common environments around red dwarfs, which present their own unique set of challenges and possibilities. This dichotomy is the very heart of Kepler's legacy. Before this telescope began its work, we could only speculate about whether planets like Earth were rare or common. The data it returned provided an emphatic answer. By observing just a tiny, single patch of the sky, Kepler found thousands of planets, allowing scientists to perform the first reliable statistical analysis of planetary demographics in the Milky Way. The conclusion was staggering. The numbers suggest that there are likely more planets than there are stars in our galaxy, and that a significant percentage of stars host rocky planets within their habitable zones. When you extrapolate those numbers across the hundreds of billions of stars in the Milky Way, you arrive at a figure that is almost too large to comprehend. Tens of billions of potentially habitable worlds could be scattered throughout our cosmic neighborhood. Kepler 1638b and Kepler 1229b are not just two individual points of light, they are statistical ambassadors. Their discovery, among thousands of others, transformed our understanding from one of hopeful speculation to one grounded in probability. The telescope's lasting gift was this shift in perspective, moving us from asking if there are other Earths to realizing with growing certainty that they are almost certainly out there in breathtaking abundance waiting for us to find them. And so we reach the 30th and final world on our incredible journey, a neighbor that brings our cosmic tour full circle, back to the very closest reaches of our galactic community. Ross 128b is a testament to the idea that sometimes the most promising worlds are not the most extreme or the most massive, but the ones that offer the gift of stability. Located a mere 11 light-years away, this Earth-sized planet orbits a red dwarf star, but this is no ordinary red dwarf. While stars like Proxima Centauri are known for their violent, planet-sterilizing flares, Ross 128 is exceptionally quiet and calm. It's a stellar pacifist, offering its planet a steady, gentle glow with very little of the magnetic tantrums that threaten so many other worlds in similar orbits. This tranquility is the single greatest advantage Ross 128b possesses. For a planet to nurture life over billion-year timescales, it needs a stable environment, and this world's parent star provides exactly that, raising the possibility that it could have held onto a protective atmosphere and maintained surface conditions suitable for liquid water for eons. The potential environment on Ross 128b is a study in serene alien beauty, because it orbits so close to its dim star to stay warm. A year there lasts just under 10 Earth days. It is also likely tidally locked, with one side perpetually facing the star and the other turned to the eternal cold of space. Yet, with a substantial atmosphere, a distinct possibility given the star's calm nature, this world could avoid the extreme temperature divides of other locked planets. Global wind patterns could circulate heat from the permanent day side to the frigid night side, potentially creating a global temperate climate, or at the very least, a wide, habitable twilight band. Imagine standing on the surface. The sky would be dominated by a deep, dark red orb, casting a perpetual sunset hue across a landscape that might feature liquid water oceans or continents. It's a vision of habitability that feels less like a desperate struggle for survival and more like a world that has enjoyed a long, quiet, and potentially fruitful history. This combination of proximity, Earth-like size, and stellar calm makes Ross 128b a crown jewel for the next generation of astronomy. It sits at the very top of the target list for future giant ground-based telescopes, like the extremely large telescope being built in Chile, and for advanced space-based observatories that will follow the James Webb Space Telescope. A primary goal for these instruments will be to do what we can only dream of today, to capture and analyze the light from the planet itself. By splitting that light into a spectrum, astronomers will search for the telltale chemical fingerprints of gases like oxygen, methane, and water vapor in its atmosphere. The detection of such biosignatures, especially in combination, would be the most profound hint of life beyond Earth we have ever encountered. Ross 128b is not just the final entry on a list. It is a beacon pointing directly to the future of our search, a nearby laboratory where the grand question of whether we are alone may one day be answered. These 30 worlds we have explored represent a breathtaking atlas of possibility, but for now they remain just that, possibilities. They are points of light whose most profound secrets are locked away in the faint whispers of starlight that reach our telescopes. The true transformation, the moment we move from simply cataloging these worlds to truly understanding them, is happening right now, propelled by a new generation of astronomical instruments with capabilities that border on science fiction. The James Webb Space Telescope is already leading this charge, acting as a cosmic chemist that can unravel the atmospheric composition of distant worlds hundreds of light years away. Its technique is as ingenious as it is delicate. When a planet transits in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere. JWST incredibly sensitive infrared instruments can capture that light and break it down into a spectrum, a unique chemical barcode. Within that barcode, astronomers can identify the fingerprints of specific molecules. The search is focused on biosignatures, combinations of gases that are difficult to explain through geological processes alone. The simultaneous presence of oxygen and methane in an atmosphere, for instance, is a powerful potential sign of life. On Earth, these gases are constantly produced and consumed by biological activity, and they react with each other so quickly that they would disappear from our air without continuous replenishment from living things. Finding such a chemical disequilibrium on a world like K218b or TRAPPIST-1e would be the most compelling hint of biology we have ever discovered, but JWST, for all its power, has its limits. It is optimized for studying planets around small, dim red dwarf stars where the transit signal is relatively stronger. To find a true Earth twin, a planet orbiting a star like our Sun, and analyze its atmosphere, we need an even more advanced tool. This is the mission of the Habitable Worlds Observatory, or HWO, a monumental project planned by NASA for the 2030s. HWO will be designed to directly image Earth-like planets. This is an astronomically difficult task. Spotting a pale blue dot next to its brilliant sun is like trying to see a firefly hovering next to a blazing searchlight from thousands of miles away. To achieve this, HWO will employ a revolutionary piece of technology called a starshade. This would be a separate, flower-shaped spacecraft that would fly tens of thousands of kilometers in front of the telescope, positioning itself perfectly to block the overwhelming glare of the star. With the starlight suppressed, the faint light reflected off the planet itself would become visible. For the first time, we wouldn't just be inferring a planet's existence from a wobble or a dimming of light. We would be taking a picture of it as a distinct world. We could observe its rotation, track its weather patterns by seeing how its brightness changes over time, and even analyze its surface for the telltale reflectance signatures of continents, oceans, and vegetation. On the ground, a parallel revolution is taking place with the construction of the extremely large telescope, the ELT, in the high deserts of Chile. This behemoth, with a primary mirror spanning 39 meters, will gather more light than all of the existing large optical telescopes combined. Its primary goal in exoplanet science will be to study the closest systems like Proxima Centauri and Ross 128 in astonishing detail. The ELT will use its immense light-gathering power and advanced adaptive optics, a system that uses lasers to create artificial guide stars to correct for the blurring effect of Earth's atmosphere in real time, to directly image planets and analyze their atmospheres. It will be powerful enough to potentially detect the atmospheric composition of a planet like Proxima Centauri b, not just during a transit, but by isolating its light from that of its star at any time. The combined power of HWO in space and the ELT on the ground will open a new chapter, moving from detecting biosignatures to searching for technosignatures, signs of advanced technology, such as industrial pollutants in an atmosphere or laser communications that would unmistakably point to an intelligent civilization. We are on the cusp of transitioning from wondering if these 30 worlds could support life to actively investigating them for evidence that they already do. But with so many potential homes for life scattered across the galaxy, our minds naturally leap to the next, even bigger question. If life is out there, what would it actually be? The field dedicated to answering this is astrobiology, and it begins with a simple but profound premise: life is tenacious. We know this because even here on Earth, in the most hostile environments we can imagine, life finds a way. These organisms, known as extremophiles, are our best guide to what might be possible on the alien worlds we've explored. Consider the microbes that thrive in the boiling, acidic hot springs of Yellowstone, or the bacteria that make a home deep inside solid rock, miles below the surface, living off chemical energy from the stone itself. There are creatures that flourish in the absolute darkness of the ocean floor, around hydrothermal vents that spew superheated, mineral-rich water into the freezing cold abyss, a complete ecosystem independent of the sun. These are not fringe oddities, they are proof that life can adapt to conditions we once thought were utterly sterile. This understanding completely transforms how we view a planet like Proxima Centauri b with its likely tidal locking. Instead of seeing a world split between a scorching dayside and a frozen nightside, astrobiologists see potential. In the permanent twilight of the Terminator line, conditions could be stable and temperate. But what about the extreme hemispheres? On the dayside, life might exist in subsurface caves or in layers of rock, protected from the direct stellar radiation. On the frigid night side, the only hope for life would be a source of internal heat, perhaps from geothermal activity, creating pockets of liquid water deep beneath the ice, much like we suspect exists on Jupiter's moon Europa. An entire biosphere on such a world might be largely subterranean or oceanic, never seeing the crimson sun that hangs in its sky. Then there are the Hycean worlds like K218b. A life form on such a planet would exist in a universe of liquid. With no land and no light penetrating from above, evolution would be driven entirely by chemistry and pressure. Life here would likely be aquatic, perhaps floating in the vast ocean or dwelling near volcanic vents on the seafloor. Without sunlight, the process of photosynthesis would be impossible. Instead, life would rely on chemosynthesis, deriving energy from chemical reactions, just as the microbes at Earth's hydrothermal vents do. These organisms could form the base of a complex food chain, supporting larger, perhaps even intelligent, creatures adapted to a life of perpetual darkness and high pressure. They might develop sophisticated forms of sonar or sensitivity to pressure changes to navigate their endless, dark ocean, their entire perception of the universe confined to the waters around them. This leads us to an even more speculative but fascinating idea. What if life elsewhere isn't even based on the same chemistry as us? All life on Earth is carbon-based. Carbon is a fantastic building block because it can form long, stable chains and complex molecules with relative ease. But could another element serve the same purpose? The most frequently discussed alternative is silicon. Silicon sits right below carbon on the periodic table, meaning it has similar bonding properties. In theory, silicon could form the backbone of complex biological molecules. However, there are significant challenges. When carbon reacts with oxygen, it produces carbon dioxide, a gas that can be easily expelled by an organism. When silicon reacts with oxygen, it produces silica sand or glass, a solid that would be rather difficult for a living creature to manage. So, while silicon-based life is a staple of science fiction, it would likely require a very different environment, perhaps one with no free oxygen or with vastly different temperatures and pressures to be feasible. The true lesson of astrobiology is that life will be shaped by its environment in ways we can only begin to imagine. On a high-gravity super-Earth like LHS 1140b, land animals would likely be stout and strong, with a low center of gravity to navigate the powerful pull. Flying creatures might be impossible, or they would need enormous wingspans to generate enough lift. In the triple star system of JJ667cc, with its varying light sources, plant-like organisms might have evolved to possess multiple types of photosynthetic pigments, changing their metabolic processes depending on which sun is dominant in the sky. Their leaves might not be green but black to absorb every possible photon from the dim red primary star, or iridescent, to reflect the sudden intense glare of the brighter companion stars. The possibilities are as endless as the number of worlds themselves. The search for habitable planets is ultimately the first step in a much grander quest, to understand not just if the universe is filled with life, but to discover the incredible, boundless forms that life can take. From the scorching inner edge of the habitable zone to the frigid, icy frontiers, from the silent glow of ancient red dwarfs to the triple sun spectacle of JJ667cc, The 30 worlds we have explored are a testament to the universe's breathtaking creativity. We have encountered super-Earths with crushing gravity and Earth twins with familiar scale, water worlds shrouded in hydrogen and frozen orbs hiding deep oceans. We have seen planets older than our solar system and others so new their stories are just beginning. This is not a catalogue of similar possibilities, but a gallery of unique experiments in planetary formation, each with its own distinct recipe for what a world can be. The sheer variety is the most powerful message of all. Nature is not trying to make copies of Earth. It is exploring every conceivable path to create an environment where the delicate chemistry of life might take hold. This incredible diversity leads to a single, profound conclusion. The universe appears to be filled with real estate that could support life. The initial question that drove this search, "Are we alone?" has been fundamentally reframed. We now know that the basic ingredients for a habitable world, rocky planets orbiting within a temperature zone where water can be liquid, are not rare treasures. They are commonplace. The Kepler telescope's statistical sensors revealed that there could be tens of billions of such planets in our galaxy alone. The cosmos is not a vast, empty desert punctuated by the occasional oasis. It is a sprawling metropolis of potential, with neighborhoods of every kind, from the quiet, ancient streets around stars like Captines to the dynamic, young districts flaring with energy. The discovery of these 30 worlds is not the end of the story, but the opening of a new chapter in human history, one where we transition from wondering about the possibility of other life to actively hunting for its signatures. This hunt is now entering its most thrilling phase, and you have a front-row seat. The James Webb Space Telescope is already peering into the atmospheres of worlds like K218b and TRAPPIST-1e, searching for the chemical whispers of biology. In the coming decade, monumental new instruments like the Extremely Large Telescope and the Habitable Worlds Observatory will push our vision even further, allowing us to directly image pale blue dots around other stars and analyze their light for signs of oceans, continents, and even the telltale markers of an industrial civilization. The greatest discovery in human history, the confirmation that we are not alone, might not be a dramatic announcement from a distant future, but a headline that breaks within our lifetimes. The evidence is mounting, the tools are unprecedented, and the targets are clearer than ever. So stay curious, follow the data as it streams in from these incredible machines at the edge of space and on remote mountaintops. The next time you look up at the night sky, remember that you are not just looking at points of light. You are looking at suns, and around those suns are worlds, watery abysses, temperate archipelagos, and ancient deserts. Each one is a question waiting for an answer. Our journey to understand our place in the cosmos is accelerating at a pace that would have been unimaginable just a generation ago. We are living in the golden age of discovery, and the next flicker of light from a distant world could change everything we know about the universe and about ourselves.